Hey guys, we'll be talking some more about terminal velocity, and this time we'll make sure all our concepts are clear. So let's start with terminal velocity again. Let's see, in the earlier video we just cleared our concept regarding a person falling, let's say, from an airplane. Let's say this is the person, or sorry, this is the airplane, and this is the person who jumped off this airplane, and this is let's say about 1600 kilometers off from the ground. The height is 1600 kilometers, and he just jumped off the airplane. What happens to him initially? Let's just revise little things here. As he jumps, his weight and air resistance both are acting on him. But initially, since the velocity is very low, and we remember that velocity, air resistance is directly proportional to velocity, as in if the velocity is less, the air resistance is less. If the velocity is more, the air resistance is more. So since the velocity initially is less when he jumps, the air resistance is less. So what happens is that weight is, let's say, 800 newtons, and the air resistance initially is just simply 10 newtons. So initially he accelerates a lot. The net force is downwards, because you can see that it's greater downwards. So the net force is downwards, and he will be accelerating with a large acceleration towards the ground, because the net force is around 790 newtons. So he would be accelerating too much. But let's say after some time, what happens is the velocity increases. The velocity increases. So because of the increase in velocity, and the velocity increases because he's accelerating. So because of the increase in velocity, the magnitude of air resistance increases a bit. It this time becomes 100 newtons. And the weight is obviously the same, 790 newtons. So let's see what is the net. The weight is 800 newtons. Let's see what is the F net now. The F net would be 690 newtons. Obviously, it's still a lot, but the acceleration would be lesser than that earlier, because the F net has decreased. You can just calculate for, let's say, if the mass is 80 kilograms. So 790 is equals to 80 A, 80 times A. F is equals to ma. So just divide for acceleration, and you will see that in this case the acceleration would be let me just divide it here. This would be 9.875 newtons. And in this case, in the second case here, this was the first case. Here the acceleration would be, the F net is 690, so 690 is equals to m times a. So 690 is equals to 80 times a. So a is equals to 690 divided by 80, which is 8.625. So the acceleration is decreasing. Although it's still accelerating, but the acceleration is decreasing with time. Now let's say, and we do not call this deceleration because there is no negative sign. It's still, and this is meter per second square, it's still acceleration, but it's just decreased from the earlier position. So this is going on, and as the speed is increasing, the velocity is increasing, the air resistance will increase, and finally it will come to a point where the air resistance of the man equals the weight of the man. So air resistance equals the weight of the man, which is, let's say, 790 newtons. So air resistance would be 790 newtons, or sorry, it was 800 newtons initially. 800 newtons. So the air resistance would become 800 newtons. At this point, the net force, or the sum of two forces, would be 0, since both the forces have balanced each other. This is a balanced force scenario. So at this point, the acceleration would become 0. So this thing, as we discussed earlier, is known as terminal velocity. This is known as terminal velocity. And if the important part that we'll be doing in this video would be to make a speed time graph of this scenario. Let's just try to make a speed time graph of this scenario. Let's say this is our axis, this is speed, meters per second, this is time. Let's say we don't know the numbers on speed time graph. We can still sketch a speed time graph, because initially we know that the acceleration was more. The acceleration was greatest initially. However, as we saw in the second step, the acceleration started decreasing, and then in the third step it would have decreased even more because of increasing velocity. So with every step, the acceleration or the tangent becomes less steeper. So it comes to this point, and eventually it comes to a horizontal. Okay, it was a fair try. Yes, it comes to a horizontal because at every point the acceleration becomes lesser than the acceleration in the previous part. So if this was 1, this was 2, and this was 3, and this was 4, because the air resistance was increasing, and so the net force was decreasing every time. This force, this constant velocity at which the object travels, once the weight and air resistance balance each other, this constant velocity is known as terminal velocity. And this is the velocity. So let's say another example, and let's try to make another velocity time graph. Let's say this is a guy, and he again fell from the plane, and this time, as soon as he fell from the plane, he opened up his parachute. This is his parachute. So initially his weight, let's say, is again 800 newtons, but initially the air resistance was, obviously it wouldn't be 10 newtons, because now there is a parachute, and we know when there is a parachute, the reason is that there is a greater surface area here, and because of this greater surface area there is more resistance acting upwards, so the speed slows down, so it becomes safer. That is why we use a parachute. So now he opens up a parachute, and suddenly his air resistance becomes around 700 newtons. However, still, if you can see, the resultant force would be downwards, because 800 minus 700 still be 100 newtons downwards. So because of that, it would still be accelerating downwards. But let's say in the second step, now because of this acceleration, his velocity increased, and he started moving at a greater velocity. And we know if the velocity increases, the air resistance increases. So if the velocity increased, his air resistance increased, to the point where the air resistance suddenly became, not suddenly, as in it would gradually become equal to the weight. The upward force balances the downward force. The weight becomes equal to the air resistance. In this case, we can say that the object has reached terminal velocity. And if I were to make a graph of this motion, it would again be very similar to the one made earlier. This is velocity in meters per second. This is time in seconds. Initially, the acceleration was the greatest in this journey. As in this journey, it was the greatest, because after that the air resistance became in the second. Let's say in the second step, the air resistance became 710. So the resultant force was 90 newtons. If you just subtract them, if this was 710, the resultant force would be 90 newtons, and the acceleration would be lesser than the one earlier. So initially the acceleration was the greatest. After that, air resistance or the upward force started increasing, and so the net force downwards started decreasing, and so the acceleration also. So the acceleration starts to decrease. You can see the gradient is decreasing throughout. The gradient is the steepest here, and then it becomes less steep, and then less steep, and then so till it comes to a point where the line becomes horizontal. This is the terminal velocity point. This is the terminal velocity point. And this velocity, we'll just read off the reading from the velocity time graph here. This velocity is known as the terminal velocity. This is the velocity at which this parachutist would be traveling once the forces have balanced. So I hope you guys understood it clearly, and how to make a motion time graph or a velocity time graph of in the situation where you have a terminal velocity case. So if there are any problems, just write them down in the comment section and I'll reply to them. I hope to see you in the next video. Thanks for watching.